Welcome back. Math 141. Today is lecture 52. We are going to do integration by parts today at some point in time. We have some WebAssign questions on substitution. We're going to start with those. If anybody comes up with any others while we're doing those and we have time, that would work out great. I just wanted to remind all those viewers out there on cable TV and all the people that happen to watch this on DVD for future semesters that NC State defeated Wake Forest this past weekend. And Wake's a very good team. So wasn't like a cakewalk, but that was a fun game to watch. So all you viewers from Wake Forest, just a reminder that you were second in that game. There were two teams in that football game, and you did well, and you placed second. But NC State placed ahead of you in that game. A couple of you was talking before class. I had a chance to work for ESPNU Saturday evening. And it's kind of an interesting job. I stand behind the two guys that are actually broadcasting the game. And I was going to bring the chart. I forgot the chart today. But I have a chart that basically has NC State defense and Wake Forest offense on one side, and I flip it over, and it's the reverse. So depending on who has the ball, I have a chart that kind of has everybody on the field who's playing. So my job is to point out who either made the pass, that's usually pretty easy, who caught the pass, or who made the tackle, or who ran the ball, or who the penalty was on, who the injured player is. So I just stand behind them and either point to it on my chart and then show it to them and then get back out of the way, or point to it on their chart. They have the same chart that I do. So it's kind of fun. And then when they have the camera on them, I have to leave. So I stand off to the side and sit on the stairs for a couple of minutes while they put the pretty people on the camera, and then I come back in and point to this person and this player and this player. And they pay me. That's kind of neat. I'd probably pay them to do the job. It's so fun. All right, now why are we here? ESPN or football or we're here for math. Yeah. Let's do math. Yeah. Russell Wilson is very good. That's all I know. Yeah. He is becoming a heck of a quarterback. All right, this is problem 9 on WebAssign. This entire set of problems for WebAssign should be some type of substitution. So we will use other patterned integration techniques. I'm actually kind of getting it looks like a little bit ahead on the syllabus, but I know what we have in front of us. There's a whole lot of stuff in section 5.7 that it's just loaded with stuff, and we have to go back into the appendix in the back of the book and pick up some of it that's not embellished the way it should be in the book, in the normal part of the book. So we're actually kind of right where we should be on the syllabus. It appears that we're a little bit ahead. Here's problem 9. I'm going to write the second term first. It's the cosine of the sine of x. And then we've got some other baggage there in the integrand. Now I know we don't deal with this stuff a lot where we have a trig function of a trig function, but it's possible to have embedded functions like that. So we don't just have the cosine of x, we have the cosine of the sine of x. So if you were evaluating that, you would put in a number, pi over 4, pi over 6, pi over 3. You'd take the sine of it, and then whatever you get for that answer, you would turn right around and take the cosine of that. So it is possible to have a function like this. Any intelligent guesses as to what we want to let u represent on this problem? Blair? Sine of x. Okay, so why does that have a pretty darn good chance of working?
Because the derivative of sine.
Because the derivative of the sine of x, our choice for u, is the cosine of x, and we've got one of those kind of out there floating by itself. So when we rewrite the problem in terms of the u substitution, we have the, what, cosine of u? and then all this stuff out here to the right is du. That's kind of a complicated original problem, but that's not a complicated version of it that we're seeing now. What's the antiderivative of the cosine of u anti-differentiated with respect to u?
Sine of u.
Sine of u plus c. It's a general antiderivative or an indefinite integral. And sine of u, this is going to look kind of awkward, but wherever we see a u, we're going to replace it with the sine of x. So instead of the sine of u, we have the sine of
Sine of x.
the sine of x plus c. And again, anytime you doubt what you have is correct, you can take the derivative of it, and you'll be back to the original integrand with the exception of dx, which is kind of a dummy variable that tells us to anti-differentiate with respect to x. Is that all right? Does that work well? Problem 11 was circled on this sheet, but I think we've set that up. Let's just kind of review what we let u represent. I think we set this up as an example problem. Anybody remember what we let u represent? Cosine of x. So with that choice, where are we headed on this integrand? This is hopefully going to be a inverse tangent. Okay? So we're kind of headed here, 1 over 1 plus u squared du. If we can get our integrand in that form, we know that integrates to inverse tangent of u plus c. Derivative of cosine of x is, so put a -1 here, a -1 here, and I think we're set, right? The numerator is 1 times du. Denominator is 1 plus u squared. We're stuck with a little -1 out in front, but that's not much to be stuck with to get it in a form where it can be integrated. We've done this, so if you write stuff down in class, check back on one of the early examples that we did, probably Wednesday or Thursday of last week. All right, the other question. Be interested in getting some of you that had some success with this problem, your thought process of how you made your decision of what to let u represent. Anybody that got this problem?
I tried to split it up.
Okay.
But I don't know.
Now you can't split it up.
Yeah.
Because you got, if it were the reciprocal, you could write each term over the single term denominator,
Yeah.
but you
Oh, you
can't
can't do that.
can't split this up in any way. Blair.
Could you let u equal x squared?
Okay, now tell me why you would want to even try that.
Because I moved the x on top to the side and just left a 1 on top, and that looks like a
Inverse tangent.
yeah.
So that x, we're going to send it out there with the dx out to the side.
And when you let x squared be, like it only goes into x to the 4th twice.
Okay.
So that would.
You know, it's in there as a factor,
Yeah.
times itself, right?
Yeah.
So we don't have any x to the 1 plus x to the 4th, but we do have, this is kind of what I was going at, but I think you did that. We have a 1 plus x squared thing here, right? And we know what that is. That's an inverse tangent. Can we kind of deal with that 1 plus x squared thing and adapt it to this problem? Yes, if it's not just x squared, if it's instead x squared squared. So that's kind of so normally we just have an x there or a u there, right? We don't have anything that has x to the 4th there, but x to the 4th happens to be x squared squared. So the choice that's been suggested is let u equal x squared. du is 2x dx. So let's go ahead and use this adapted version of the original problem. Any corrections, compensations, any of that?
1/2 in front.
Good. Need to multiply by 2 and multiply by 1/2. So we're stuck with a 1/2 out in front, and we're hoping then that all this is 1 plus x squared squared becomes u squared. That looks a whole lot better. And all of that underlined stuff is, that's du. And that worked, right? We thought it had a chance of working, but it in fact actually worked. This integrand, I told you we'd see this one a lot more than inverse sine. This integrand is actually the derivative of inverse tangent, so we're anti-differentiating that. So we ought to be back to inverse tangent. Instead of inverse tangent of u, it's inverse tangent of x squared. Does that work? Anything else from that WebAssign that is due tomorrow?
What number was that?
This was problem 12. I think these are all the same. I don't know if they have any randomized variables in them. Sometimes I can't tell by looking at them. But if yours is slightly different from this, this would probably be the method that would get it integrated. Anything else? Pass that back all the way to the back. That's Catherine's. All right, well, let's go on to another type of pattern integration, which is integration by parts. So we are going to identify part of the integrand as something and the other part as something else. So we basically divide the integrand into two parts. So by parts is kind of how we actually approach this. If you know the product rule, all we have to do is kind of throw the product rule in reverse, and we have this rule, this integration by parts technique. Now, and I probably wouldn't choose these letters personally, but these are the letters that are used in the book, so let me use the same letters that are in the book. They use a U and a V, and my U's sometimes might look like my V's, which is probably the case with you also, but I'm trying to use the same letters that are in the book. So if one of the things in the product is U and the other is V, they're really functions of X. How does the derivative of a product actually work? First times derivative of second, right? Plus second times derivative of first. Actually, I'm going to write that slightly different. So V prime I'm going to call derivative of V. If you've used this particular technique before, you kind of know where this is headed. And V times for U prime, I'm going to put in derivative of U. One of these we want to send to the other side, so I know kind of where I want to end up with this. It really doesn't matter, but if I want to make this formula match what's in the book, I'm going to send this term to the other side. So I've got derivative of U times V minus V times du. This was positive over here, so I'm sending it to the other side, so now it's negative. And this term is by itself. So it's a product rule. One of the terms sent to the other side, if these two things are equal, which they are, then we ought to be able to integrate both sides, and they ought to still be equal. So to integrate the left side, we can integrate each piece of it. This is a self-answering question. What's the integral of the derivative of something? Whatever that something happens to be.
Yeah.
And then we've got to integrate v du. I don't know what that is. Now that doesn't look like that's like we've gotten to a place where we want to use it, but this is our technique, our kind of general rule for integration by parts. So we're going to look at an integral that is in this form. Part of the integrand we're going to identify as u, and the other part, and we have to accommodate everything that's in the integrand. The rest of the integrand is going to be dv. And if we can if we can identify the two parts of the integrand, part of it is u and the rest of it is dv, here's how we can approach that problem that might actually help us get it integrated. So how might this help? So the first time we visit the problem, it's in this form, u times dv. We identify those things. We know that from the equation we just had, it is uv minus v du. So we're hoping that the next time we visit this, this isn't an issue. There's nothing to integrate here. That's part of the answer. But the next time we switch it into this new form, instead of having u times dv, it might be easier to deal with if it's in the form of v times du. I know that probably doesn't, if you've never used this technique, that probably doesn't mean a whole lot. But that is the kind of the good thing about this, is that we have a new integral problem that is potentially substantially different from what we started with. And if this is a difficult problem, maybe this one will be much easier. So this is integration by parts, and here's where we're going to start. So again, as is the case with substitution, probably the best thing to do is see how this plays out in several examples. And the example problems here are about as diverse and different as the ones we looked at with substitution. All right, first example. And I guess we probably ought to cover the fact that if we could do this problem with substitution, since we just finished doing substitution, and I think all of you feel reasonably comfortable with it, let's go ahead and use substitution, because we all feel pretty good with that. Substitution won't solve this problem, right?
Mm-hmm.
You see why not? I mean, what are we going to let u, if we're doing this by substitution, what are we going to let u represent? Sine of x. Okay, how do we deal with x? I don't think we could do that with either u or du, right? This is not going to work. If we let u equal sine of x, derivative of u is cosine of x dx. Well, that's not anywhere to be seen here, right? What if we let u equal, this isn't going to work either. What if we let u equal x? Derivative of u is 1 dx. How do we accommodate that? So substitution, normal substitution, isn't going to work. And that's going to be the case with most of these. Now, one of the questions you're going to have before we finish today is, how am I going to know? I don't want to waste time trying substitution if, in fact, substitution's not going to work. Hopefully, after we do several examples, you'll be able to look at this and say, I mean, just a few seconds. If I let u equal sine of x, am I going to be able to accommodate that? No. If I let u equal x, am I going to be able to accommodate that? So it's not like you're going to waste 6 minutes and then all of a sudden it doesn't get you anywhere. It should be a matter of seconds to know that substitution is not going to work. So we're going to use this particular fact, this technique. So we're going to identify, probably ought to start another sheet here. And let me rewrite kind of where we're headed. Part of the integrand is going to be u. The other part is going to be derivative of v. We can do that. Then the next time we have to visit it, it's in the form of v du. So the thing that we call u, when we look at it again, it's actually going to be changed. It's going to be du. That's probably the main advantage of this technique, is the thing we identify as u, when we revisit it, it will no longer be u, but rather the derivative of u. So we are going to be kind of doing both things in this problem, integrating and differentiating. So I kind of, as I work down the page, I'm going to be differentiating. If I work up the page, I'm going to be anti-differentiating. But you don't have to do the problem this way. You set up your own organization. So if I choose x to be u, the next time I have to visit that, it's no longer going to be x. It's going to be the derivative of x, which that's kind of nice, right? Derivative of x is 1. So I'm liking the way that has a chance of working in this problem. So with u equal to x, what's the derivative of u? 1
dx.
dx. Okay, and that's got some merit here. Might work. Well, everything else has got to be dv, because whatever we identify u and dv to be, we've got to accommodate the entire integrand. So if u is equal to x, then everything else has got to be dv. So that's the derivative of v. So to get v, we've got to anti-differentiate. So I'm working up the page now. So I'm anti-differentiating. What has sine of x dx for its derivative?
Cosine dv.
Negative cosine of x.
dv. I know.
Now, we could have a plus c, right? Yeah, since it's a general anti-differentiation, that is not necessary. It's not going to change the final answer to the problem. All right, so let's use this. We have it in the form of u dv. How many of you have done integration by parts before? Okay, about a fourth of you. Okay. So the first part of the answer is u times v. So what is that for us? U is x. V is negative cosine of x. There's nothing to do with that except write it down. That's part of the answer. Now, we still have another integral problem to do, but hopefully it's different, and hopefully it's easier than what we started with. V times du. So we've got minus a negative, which is plus. I like that. That's going to work, isn't it?
Mm-hmm.
So we started with something that by itself was not integrable. Now we've done this little massaging with this particular technique, integration by parts. The next time we visit something that we have to integrate, this is a doable problem, right? What's the antiderivative of cosine of x dx? Sine. End of problem. Is that all right? As hard as substitution, or equally difficult or harder? I don't know. Some of them are worse. This one's not worse. This one's probably better or easier than most substitution problems. Any question about any part of that?
How do you know which one to let u equal what to let v use?
That's
like, would it matter if you switched it?
Yes. In fact, if we let u equal sine of x, let's think through that a second. So we're going to let u equal sine of x. The next time we visit that, it's going to be du. What's the derivative of sine? Didn't really get a whole lot better, did it? It was a sine, and now it's a cosine. So we're kind of stuck in the same thing. So you'll know when before you get to this stage, you'll know right here if things got better or things got worse. If they get worse, it's a pretty good indicator you need to make the other choice. Usually there's only one other choice. And when I mean worse, if you're still stuck with a trig function, but you've got x to a higher power, you've got x squared instead of x, that's worse. That's not better.
If it gets worse, though, couldn't you just switch the integrals?
Switch the integral.
Because remember, we just chose one to move to the other side. Couldn't we move the other one instead?
Well, we've started the equation in this form. I don't know that we'd want to work backward from this, because we've already taken the time to figure out u and v, and then v d. I don't think we want to try to switch it and go the other direction. I think as we do more examples, that choice is going to be more clear to you. All right, so we want to use So we're going to make a choice. Here's kind of where we are now. We're going to make a choice for u. And the next time we visit that, as far as having to do a problem ourselves, it's going to be du. Do you see either of these two? These kind of two choices, right? This or this? Do you see either of those kind of staying the same or one of them getting a little better?
You did the x.
If we do x squared for u, when we visit it again, it's no longer going to be x squared. It's going to be 2x. So the x squared got reduced or knocked down to x. Not that we can finish the problem, but it's better. So if we let u equal x squared, dv is everything else. So as you write down what du is, you're going to have an idea, a general idea, that this has a chance of working. Derivative of u is 2x dx. Now we're working up the page. You can do it differently. It's your choice, but I like to be doing differentiating as I work down the page. If I go from dv to v, I'm anti-differentiating. I'm going up the page. What has e to the x dx for its derivative?
E to the x.
That'd be e to the x. Let's see what this looks like. So it should be uv nothing to do there except write it down. That's part of the answer. Minus the integral of v du. So are we better than we were when we started this problem? We started with x squared e to the x. Don't let the 2 get in the way. You can, in fact, just move the 2 out in front, right? So are we better off than when we started?
Yes.
But we're still not able to get this problem done. This happens sometimes in integration by parts.
Do it again.
Do it again. Now, do you sense that it's going to be workable, doable when we do it again?
Yeah.
Mm-hmm.
Yes.
Yeah, the first time we knocked x squared down to x, the next time we're going to knock x down to 1. So it's going to be a workable problem. So that's where we are the first time through. So we've already got x squared e to the x as part of the answer. So now we're going to take this and do integration by parts again. So if you use lowercase letters up here, maybe you can use capital letters here, or you can whatever. So I'm going to say capital U is what? X. And derivative of capital V is
1 dx. Oh,
E
to
e to the x,
to the x.
dx. Derivative of capital U is 1 dx, and capital V is
the x.
e to the x. So x squared e to the x is part of the answer. We've got a minus 2, and now we kind of do the whole thing over again. So we're going to do this. Now we're with capital letters, but it's the same stuff. So what is it? UV, capital U, capital V, x, e to the x, minus capital V, derivative of capital U. Capital V is e to the x.
Dx.
Derivative of capital U is 1 dx. I'm not going to write the 1 down. Can we finish this problem now, kind of without any special technique?
Yes.
We can anti-differentiate e to the x with respect to x. So that is not uncommon at all to kind of work your way down, knocking x squared down to x and then x down to a constant, as it happened in this problem. So I've got minus 2 of those. I've got minus 2 times this minus, which is plus 2. What's the antiderivative of e to the x with respect to x?
E to the x.
E to the x plus c. Does that work?
Mm-hmm.
Suppose this original problem had been x cubed. What would that mean?
Do it 3 times.
You'd have to go through this iteration 3 times, right? And each time you go through it, you knock the degree of x down 1 time. So that's a little bit of a pain, but at least you know that eventually you could get there with that kind of reduction approach. Questions about this one? Now, in this one, we know that we could knock x squared down 1 degree as we go. We know that e to the x wouldn't work like that. We can't knock it down as you go because the derivative of e to the x is itself. So what if we have this is probably the strangest thing that can happen. But integration by parts will still get us an answer to this problem, even though it doesn't seem like it's going to give us an answer. We're not going to be able to reduce that if we let that equal u, because it's its own derivative multiple times. We're not going to be able to reduce that because derivative of sine is cosine, derivative of cosine is back to sine, so you're alternating between sines and cosines. So let's let u equal one or the other. In fact, it doesn't matter in this problem. Derivative of v is everything else. And none of us think that it's going to work at this point in time on this problem. I actually kind of have a general idea that it will work because I've done this problem many times before, but what has worked to this point in time, it's not going to work the same way. Derivative of e to the x
A to the x. Yeah.
is itself. Antiderivative of dv, because we want to go back to v, what has sine for its derivative?
Cosine.
Negative.
Negative
Yeah.
cosine. So here's our original problem. We're doing this technique, integration by parts, so it's uv minus the integral of v du. Minus this negative is plus. Is that any better than what we started with?
No.
Here's what we started with, e to the x sine of x. Oh, that's a great change. E to the x cosine of x. That's kind of the same situation we started with. So let's take this thing and do integration by parts again. Let's use the capital letters. And let's kind of make the same choice or similar choices. Up here we let u equal e to the x. Derivative of capital V is everything else. If u is going to be e to the x, what's derivative of capital U? And if this is derivative of capital V,
Sine of x.
capital V is its antiderivative. I do have a method why I'm rewriting the whole equation every time, in case you're wondering if I've kind of lost it a little bit. All right, so the framed part is the second version of integration by parts. So it ought to be, what, uv I'll put this in brackets. This is our latest iteration of integration by parts. uv minus the integral of v du. That is great. Are we right back where we started?
Yeah. Kind
We started with e to the x sine of x, and oh, look at this. We have another e to the x sine of x. What makes this problem work?
Can cancel out.
We put some terms
Divide.
together.
Oh.
This sign right here actually makes this problem work. Because if I want to get rid of minus this integral, what can I do? Add that integral. So I add that integral to this side. I don't think we've ever done anything quite like this before in here. So we have this equation. Here's our equal sign. So we did the same thing to the left side and the right side. Minus this integral plus this integral. They knock each other out. The right side looks good. Because we got rid of that. What is anything added to itself? You have two of those. So now we have 2 e to the x sine of x. Is that all right with everybody? Anything added to itself, you have 2 of those. We don't want to know what 2 of those happens to be. We'd want to know what 1 of those is. Wasn't that our original problem?
Divide by 2.
Here's the original problem right here. What's the integral of e to the x sine of x? At this point in time, we have twice what we started with. We don't want twice what we started with. We want to know what is the integrand that we started with. So take half of each side. So 2 loops of integration by parts. We seem to be right back where we started. In fact, we were in terms of the integrand. Add it to both sides. Anything added to itself, you have 2 of those. Final thing is to divide both sides by 2. So did we solve the problem that we started with? Yes. This is the solution. Questions on that? That's kind of awkward.
If you take the derivative of that on the right side, where you get the integrand.
That's exactly right.
Oh.
If you took the derivative of this, which you can probably tell me what's going to happen if you would take the derivative of this, and you're supposed to end up with this. Apparently some of those terms that you get with the product rule, they must knock each other out, and you're left with just one of them. So you could check that, but that's going to take more than a few seconds to check. All right, probably enough for one example. Let me make it a good one here. Log, inverse tangent. The others we'll get to tomorrow, but take a few seconds and just write down on your paper what you want u to represent. Remember, the next time you visit it, it's in the form of du. And what you want dv to be. All right, I'm going to stop you. How many of you let u equal x? Is that going to work? What's the problem with that? Let's just write it down. It's not going to work. Let's let u equal x. Everything else should be the derivative of v. Now, if you chose u equal to x, it's not like you're a horrible person and you just can't think at all. You probably chose that for the reason the next time you'd visit that, it would be du, and that's better because 1 is better than x. Here's why it's not going to work. We've got to anti-differentiate the natural log of x. Do we know of anything that we could take its derivative and get the natural log of x? We know how to take the derivative of the natural log of x, but can we take the derivative of something and get the natural log of x?
Yeah.
It's not going to work. So even though we kind of chose it, if you made that choice, I know why you chose that. It's for the right reason. But when we get here to try to anti-differentiate natural log, it's not going to work. So as is the case with some math problems, we don't fuss and whine and cry about the fact that it didn't get us anywhere. This is one of the joys of beauties of doing mathematics. It wasn't seeming to work, so we make another choice. We continue to do battle with the problem. I can see that all of you share that emotion with me. That's the joy and beauty of mathematics. So we don't have much of a choice here. What's the other choice? Let u equal natural log. What's the derivative of natural log?
1 over x.
1 over x. So everything else should be dv. So x dx is dv. We have to anti-differentiate that to get back to v. What's the antiderivative of x?
1.
1/2 x squared.
Oh, man.
All right, let's see what we have. uv that'll never, I mean, you just write those down. That's never going to tell you if it's going to work or not. Here's where we know if it's going to work or not, is the last part, which is what? V du? We can put those together, right? Division by 2, we can bring out front. And what's x squared divided by x? It's just x, right? Can we finish that problem with other patterned techniques that we have prior to integration by parts? We can.
Wouldn't v be x though, and dv be x squared divided by 2?
Well, the thing that makes this work is you combine those. X squared over 2 times 1 over x. Before we do any anti-differentiation, things that you can combine, you should go ahead and combine.
No, but I mean like in the step above it.
Up here?
Like where you did your
Right
v?
here.
Yeah.
Okay.
Why isn't your v your x? Because that's in your problem.
Well, the problem, everything that's in here has got to be u or dv, right? Because that's our rule. That's our technique. The integral of u dv is uv minus v du. So I think we've got it taken care of in u and dv. And the other way failed, so that this, if it's going to work at all, it's got to work in this direction. So natural log of x, x squared over 2, this 1/2 that comes along for the ride, what's the antiderivative of x with respect to x?
X squared over 2.
X squared over 2 plus c. Does that work? Mm-hmm. Now there's some other kind of strange looking integrands that we'll try to tackle with this technique, and we'll look at some of those tomorrow. See you tomorrow.